Okay, so now what we're going to talk about is section 3.2, which is entitled Inverse Functions. Chapter 3 is about exponential functions, and then we're going to study what are called logarithmic functions. And it turns out that exponential functions and logarithmic functions are related to each other, and specifically they're what are called inverse functions of each other. And before we begin talking about inverse functions are functions that have what is called an inverse, satisfy a special property called one-to-one. So if a function has an inverse, and we're going to see this later, there's a theorem that says if a function is one-to-one on its domain, then an inverse function exists. So first I'm going to talk about one-to-one. So reading the definition carefully, a function f is one-to-one on a domain D if each output value f of x corresponds or comes from exactly one value in the domain. So more formally, f is one-to-one if the outputs f of x1 and f of x2 are not equal whenever the inputs are not equal. There's another way to say this, and we'll use this in the next part. Equivalently, f is 1-to-1 if f of a is equal to f of b. Okay, the only way that two outputs can be equal, so if f of a equals f of b, then a has to equal b. Okay, so we're going to verify in just a minute. We're going to look at two functions algebraically. I'm going to show you how to show that those functions are one-to-one. Okay, so I'm going to use this property right here. Okay, so if f of a equals f of b, the only way that two outputs can be the same is if really the inputs are the same. And a function that is one-to-one, so if you remember, the way you can know if a graph is a function, it has to pass the vertical line test. Okay, so once you know it passes the vertical line test, the function is said to be one-to-one if it passes the horizontal line test, which says that every horizontal line can only intersect the graph of a one-to-one function at most one time. So, for example, if I look at something really simple, if I look at f of x equals x squared, and that function has domain all real numbers. If we take a look at the graph of x squared, okay, it's a parabola that goes through the origin. The graph has this shape, and what you're going to notice, let me change colors here. Okay. If I draw a horizontal line, you're going to notice that the function is intersected on its graph twice. Okay, so if I say that's x1 and I say this is x2, right, f of x1 is equal to f of x2, but x1 and x2 are different to each other. Okay, so specifically, that's violating this rule right here. Right, whenever the inputs are different, you're supposed to get different outputs. So, right, whenever x1 is not equal to x2, the outputs are supposed to be different. And what's happening for this function is x1 does not equal x2, but the outputs are the same. This happens for, like, say, f of 1 is the same as f of minus 1 because 1 squared is the same as negative 1 squared. Okay. So any function that does not pass the horizontal line test is really violating the property of a one-to-one function. Now, there are other functions that are one-to-one, so like f of x equals x cubed. On its domain, the graph looks something like this. And what you'll notice is no matter where I draw horizontal lines, you're only going to intersect the graph at most one time. So this function is 1 to 1. It passes the horizontal line test. And like I said, later that's going to mean that the function has an inverse. Okay, so let me show you. It's pretty easy to look at a graph and tell if a function is 1 to 1 because you just have to make sure that no horizontal line intersects more than once. But what if I just have the algebraic expression and I don't actually have its graph? Okay, so let me show you how to algebraically show that a function is 1 to 1. Okay, so example 1, we're going to show that f of x equals 4 over x minus 2 is a 1 to 1 function. So what you do is, what I want to show is that if I set f of a equal to f of b, I want to show that if f of a equals f of b, then the only way that can happen is if a and b are the same. Okay, so suppose f of a equals f of b, and then what that implies is, well, the function, remember f of x is 4 over x minus 2, so f of a is 4 over a minus 2, and I'm setting that equal to f of b, which is 4 over b minus 2. And then I'm just going to do cross multiplication here. So I'm going to do the cross multiplication. So that means that 4 times b minus 2 has to equal 4 times a minus 2. And then I'm going to divide both sides by 4. So that's going to cancel the 4's on both sides. And I just get b minus 2 equals a minus 2. And then I'm going to add 2 to both sides. That's going to get rid of my minus 2's. And the result there would be that a equals b. Hence, f of x equals 4 over x minus 2 is 1 to 1. Okay. Sorry, I ran out of room there. Maybe I can just rewrite that. It's 1 to 1. Okay, and if you go to Desmos and you graph 4 over x minus 2, you will see that the graph does pass the horizontal line test. Okay, so how about showing that something is not 1 to 1 algebraically? Okay, so determine if the function g of x equals x squared minus 4 is 1 to 1. Well, first of all, you can look at its graph. Actually, let me redraw this. If I go down 1, 2, 3, 4 units, remember, x squared minus 4 is just x squared shifted down 2 units. Now, ignoring the scaling, it's going to be a parabola opening upward like this, and there's lots of horizontal lines I can test this with, but if you look, you can find horizontal lines that intersect the function more than once. So I know this is not a 1-to-1 function, but how do I do that without looking at the graph? Okay, so let's go ahead and do the same thing as in the previous problem. Let's assume that, and the function's not f anymore. Now this time the function's g, so assume g of a equals g of b. And what that means is that, so g of a is a squared minus 4, and I'm setting that equal to b squared minus 4. Now I'm going to add 4 to both sides. That'll cancel the minus 4's. And now I know that a squared is equal to b squared. But now if I take the square root of both sides, a doesn't necessarily have to equal b. G of a will equal g of b as long as a is, if you take the square root of both sides, that says that a can be either the plus b or minus b. And right away that tells me that g is, we didn't get that a is exactly b, so g is not 1, 2, 1. You can also show it's not 1 to 1 just by noticing that g of 2 is the same as g of negative 2, but 2 is not, the inputs are different, but you're getting the same outputs, right? Like this right here is 2 squared minus 4, which is 0, and this is negative 2 squared minus 4, which is also 0. Okay, so you can show something is not 1 to 1 just by showing that when you plug two different numbers into the function, you're getting the same output. In this case, 0. But this whole process right here is how you can show that a function is, well, it's the process you use to show that a function is or is not 1 to 1. So if you set g of a equal to g of b, or f of a equals f of b, you do the algebra. If you can show that a is identically b, the function would be 1 to 1. But in this case, a could be either b or minus b, hence g is not 1 to 1. And you can see that down here, right? If this was a over here, b would equal minus a. Okay, so if a is 2, b is going to be negative 2. And when the function outputs are equal, but the inputs are not the same, that's telling us that it's not 1 to 1, it's failing the horizontal line test. Okay, so example 2, I've got this polynomial function right here, so now I'm just using the horizontal line test to determine if a function is 1 to 1. And for the first function, x cubed plus x squared plus 2x plus 1, you can use Desmos to plot it. Here I've just used what's called Mathematica to plot this. And if I'm testing to see if it's 1 to 1, I'm just thinking about all possible vertical lines. And what you'll notice is that any not vertical lines, I apologize. I'm looking at a collection of horizontal lines. And you'll notice that no matter which horizontal line that you draw, you're only going to intersect the graph at most once. So in this case, f is a 1 to 1 function. Right? It passes the horizontal line test. Okay. Okay, but part B, okay, so now if I look at the function g of x equals x cubed plus 3x squared plus x minus 2. Now, to show something's not 1 to 1, I just have to find one horizontal line, and I found one right here, that actually intersects the function 3 times. So I would say, sorry, not f, I would say g is not 1 to 1. G fails the horizontal line test. Okay, that's supposed to be an I right there. There we go. So G fails the horizontal line test, so it is not a 1 to 1 function. Okay. Okay. So what we're really interested here is we're interested in inverse functions, and just read through the definition here with me. It's given a function f, its inverse, if it has one, is a function f to the minus 1. Okay, now I want to make something very clear. F is not a number, so when I'm writing negative 1 power, just be careful. Like, if a is a number, a to the minus 1 is 1 over a. Okay, but if f is a function, f to the minus 1, this wouldn't even really make any sense. It's not really the reciprocal 1 over f. So just make sure that you understand the context. When you write f with a -1 power, or I would say superscript, that's really just notation for what's called the inverse function. And the way it works is, and I'll just rewrite it here on the side. So I'm not really sure where I lost everybody there. I just noticed my video was paused. So one thing I was talking about was the way the inverse is defined is if y equals f of x. Okay, so if x is the input and y is the output, what the inverse function does is if y is the output, it becomes the input of the inverse, and the input becomes the output. And what that means graphically down here is if you took a point on the graph of f, so if xy is on the graph of f, one way you could graph the inverse function is just swapping the coordinates. So if xy is on the graph of f, then y comma x is on the graph of f inverse. And then the other thing I was saying was I boxed, in the theorem, I boxed this condition that's true. When you compose a function with its inverse, they kind of cancel each other out or undo each other, like tying your shoes and untying your shoes. So if I compose the inverse function with f of x, you just get the input x back, and if I compose f with the inverse function and I plug in y, I just get y back. Okay. Okay. So example 3, the graph of a one-to-one function f is shown below, and if you look at that graph, I think you can convince yourself it passes the horizontal line test, so it is a one-to-one function. And I want to find the domain and range of the inverse function. Okay, so what I'm going to do is for f, okay, looking at the graph, the domain, the x coordinates on the graph range from -1 to +2. In the range of f, the lowest y coordinate is -3, and you get all y values up to +3. So for the inverse function, the domains and ranges just swap each other. So the inverse function has domain -3 to 3, and the range becomes -1 to 2. Okay, and again, this should make sense. If all that's happening, going from an original function to its inverse, is the outputs are now the inputs, and the inputs are the outputs, right? The domain is just all the x-coordinates. Right? So all the x-coordinates of the original graph now become the y values, and all the y values of the original graph now become the inputs, or the x values. Okay, so there's the domain and range for the inverse function. And then now what I'm going to go ahead and do is I'm actually going to graph the inverse function. And the way we're going to accomplish this is I'm just going to look at the graph, and I'm going to look at maybe 3 special points. I'll probably look at these 3 points right here. Okay, so on the graph of f, I've got a set of x and y values. So those 3 points have x coordinates -1, 1, and +2. And the corresponding y coordinates are -3, -1.5, and when you plug 2 in, you get 3. Now, on the graph of the inverse function, all that's happening is the x and y values are swapping. Okay, so I'm just swapping all the coordinates, and then I'll plot those points. So I can go 3 to the left and down 1. I can go right 1 and down 1.5, which actually lands me on the same point. Then I can go 3 units to the right and up 2. What did I do wrong? Oh, I see what I did wrong. That makes sense. Hold on. I gotta redo this. What you'll notice is I screwed up on the point in the middle. The input became minus 1.5 and the output changes to 1. So I'd still have the point -3, -1. I didn't screw that up. Okay. And then I have the point minus 1.5 comma positive 1, which would be right here. And then I can go right 3 and up 2. And the graph of the inverse function looks something like that. So this is f, and this is f inverse. Now I want to point out a special property to everybody. What I'm going to do is I'm going to plot a particular line. Okay. Now, what I've graphed here, this is the line y equals x. Okay. Now, since the x and y coordinates are swapping, to go from a graph of a function to its inverse, okay, the graph of f or let me say it this way. The graph of f inverse, sorry, it's really hard for me to write with this pen sometimes. The graph of f inverse is the graph of f reflected over the line y equals x. Okay, so hopefully you can see that, right? If I look right here, hopefully you can convince yourself that this point on f was reflected over the line y equals x to get this point up here. So that's one way you can get the graph of an inverse function, is really think of it as the reflection over the line y equals x. Now, and again, just if you're going to graph an inverse function from an original graph, you would pick some points on the graph of f as I did. You would switch the x and the y coordinates, plot those new points, draw a curve through them, and that's how you get the graph of the inverse. Okay, so that's how you do it graphically. Now, if I'm given an algebraic expression, how do I find the inverse? Okay, how do I find the equation of the inverse function? So that's what we're going to do next. Okay, so here's the procedure. So, first of all, you have to suppose f is 1 to 1 on an interval I. Okay, so the original function has to be 1 to 1. And then how you solve for the inverse is you're going to first solve the equation f of x equals y for x. Okay, so down here what you're going to do is we're going to solve f of x equals y, which is the equation. Okay, so 3x plus 2 is f of x. So basically you're setting your function equal to y and then solving for x. Okay, now you're going to subtract 2 from both sides to get 3x equals y minus 2. And then I'm going to divide by 3 on both sides. X is going to be y minus 2 over 3. And then notice what step 2 says. Step 2 says to replace x with the notation f inverse of y, and I get y minus 2 over 3. Okay. So our textbook always has you write the inverse function as a function of y. Now you could use any letter you want, right? If I was being weird here, I could switch it back and just write f inverse of x equals x minus 2 over 3, or I could be weird, I could say f inverse of z equals z minus 2 over 3. Doesn't really matter which variable I use, it's just that in the textbook they, for some reason, always use y as the input of an inverse function. Okay, so moving on to the next one. 3x plus 2 is just a line. It turns out that y minus 2 over 3 is also just a line. So the inverse of a line is a line. So not really a big surprise there. Okay, so let's go to the next one. Actually, one interesting thing actually is I could go to Desmos. So before I do this next part, I'm going to do this. I'm going to graph the original function 3x plus 2, and then I'm going to graph the inverse, which was, I'm going to use the variable x this time, it's x minus 2 over 3. And then remember, those are supposed to be the reflections of each other over the line y equals x. So hopefully you can buy that. If you look at the original function 3x plus 2, that's the red graph. And I look at its inverse, which is, in terms of x, x minus 2 over 3. And then I've also plotted the graph of the equation y equals x. And I think you can convince yourself that the blue graph is obtained from the red graph by reflecting over that line y equals x. So I just wanted to show you the graphical connection between a function and its inverse. Okay, so back to the handout. Okay, so let's look at part B. Now I'm going to do a little bit more than is asked on this one. I'm actually going to find I'm going to look at the domain and the range of g of x. Now this is a function that involves a square root, and so before I actually find the inverse function, I just want everybody to note or notice okay. So hopefully everybody saw part A. Hopefully I didn't accidentally pause the video. But here's part B. So finding the inverse function of g of x. So first of all, I want you to notice that I'm going to find the domain. 4 minus 2x has to be greater than or equal to 0. And if you add 2x and divide by 4, you actually will get that x has to be less than or equal to 2 for this to work. Okay, otherwise 4 minus 2x would be negative. So just keep in mind the domain would be negative infinity to 2 of the original function. And this is harder to probably argue, but if you ignore the minus 2, okay, if I just look at the square root part right here, the square root of any number is 0 or bigger, and then by subtracting 2, hopefully you can convince yourself the range would be minus 2 to infinity. Okay, so that'll be important. We're gonna, after I find the inverse function, we're gonna graph. I'm gonna show you what the graphs would both look like. Okay, so step 1, or the first part, is always to take your function and set it equal to a variable y. And then I'm going to start solving for y. So I'm going to add 2 to both sides. 4 minus 2x is going to equal y plus 2. Okay. And the next thing you have to do to get rid of the square root, you have to square both sides. Oops. So the right side would become y plus 2 squared. And now I can subtract 4, and I can multiply both sides by negative 1/2. So first I'll subtract 4 from both sides, and I'll get negative 2x equals y plus 2 squared minus 4. Okay. And then I can multiply both sides by negative 1/2. So this would be, and the negative 1/2 has to be both multiplied by both terms on the right. So negative 1/2 times y plus 2 squared, and then a negative 1/2 times negative 4 would give you a plus 2. And then finally the last step then, replace x with f inverse of y, and this would be the inverse function. And I'll write down the domain and range. So remember, the domain and range swap, so the domain is the range of the original function, and the range is the domain of the original function, which was negative infinity to positive 2. Okay, so there's my inverse function, and the domain and range is just the domain and range of the original function swapped. Now, I'm going to go ahead and plot this on Desmos. Okay. So let's go ahead and do that. Okay, so I'll go to Desmos. Let me clear these out. And the original function was the square root of 4 minus 2x, and then minus 2. So there's the original function. And the inverse, if I write it in terms of x, so you can just change the y to an x here. Now, notice the inverse function is a quadratic, and typically a quadratic's domain would be all real numbers, but in this case, let me see if I remember how to do this even. I guess the domain is x is greater than or equal to negative 2. There we go. Alright. And then of course, then I'll also graph the line y equals x. So now you have to be really careful. If your original function is a square root function, your inverse will be quadratic, but it's not going to be the whole quadratic function. It's actually going to be either the right half of the parabola or the left half of the parabola if you break it up at its vertex. So this point right here is actually the vertex of the inverse function. Right? If I look here, if I get rid of that condition, the whole graph of the inverse function, since it's quadratic, it's not really one-to-one. So that's why what I'm doing here is I'm specifying that x has to be greater than or equal to minus 2. And then I'm only looking at the part of the graph that is the inverse function. And if you look here, hopefully again you can convince yourself that the way I get from the red graph to the blue or purple graph is by reflecting over that line y equals x. Okay. So now for the next part. Okay, now I want to find the inverse of h of x equals 2 minus x minus 2 squared. Now again, this function is quadratic, and let me just draw the graph of the function h real quick for everybody. Okay, or actually before I even do that, let me rewrite h in transformation form. I noticed my video paused on me again, so I might be repeating myself. So what I did was I took h of x and I rearranged the terms and wrote it as minus x minus 2 squared plus 2. Okay, and the vertex would be the point 2, 2. And now, if I go 2 to the right and up 2, there would be the vertex. And this negative leading coefficient tells me that the parabola opens downward. And then what I explained was, this is why I had to specify that x was less than or equal to negative 2. If you look at the graph as written on the right, you'll notice that, okay, it doesn't pass the horizontal line test, so it's not 1 to 1. Okay, but what happens is if you erase the right half of the graph, okay, and if I only look to the left of the vertex, okay, if I'm restricting the domain, okay, now the graph of just the left side of the parabola is a 1 to 1 function, so it does have an inverse. And then the other thing I did was, looking at that graph, the domain and range would both be minus infinity to positive 2. The inverse function swaps the domain and range. Since they're both the same, you're going to have the same domain and range for the inverse. So let's go ahead and find the inverse of this function. Okay, so again, I'm just going to write this down. The domain and the range are the same. They're both minus infinity to positive 2. And then step 1 is to take the function, set it equal to y, and then you're going to solve for x. So now, first thing I'm going to do is I'm going to subtract 2 from both sides. So I get minus x minus 2 squared equals y minus 2. Then you can both multiply both sides by negative 1. So x minus 2 squared, multiply both terms on the right by minus 1, and you'll end up getting a positive 2 and a minus y. And then now I need to get rid of this square right here. And how do we undo a square? Well, I'm just going to square root both sides. If I square root the left, I get x minus 2. But be careful, because on the right, when you take a square root of both sides, you pick up a plus or minus. Now I can add 2 to both sides. So I'd get 2 plus or minus the square root of 2 minus y. And this might be one of the harder parts, is you can't have both the plus and the minus, because otherwise each y value would give you 2 different x values. So I have to choose the plus or the minus. This is where the domain and range of the original function come into play. Okay, so x can only be 2 or less. The only way for x to be 2 or smaller is if you choose the negative sign. Okay, the square root of 2 minus y for the appropriate y values is going to be positive, so I have to make sure that my x values are 2 or smaller, I have to choose the negative sign. And then the last step would be replacing x with h inverse of y, and that would be 2 minus the square root of 2 minus y. Okay. Then the domain and the range are still the same as they were before, which is minus infinity to 2. And you could go graph both these functions in Desmos and notice that one function is the reflection of the other over the line y equals x. Okay, so now last part, one more problem. So one more example finding an inverse function. So I'm going to show that the function is 1 to 1. Then I'm going to go ahead and I'm going to find the inverse. And I'm also going to find the domain and range of both functions for this case too. So what I'm going to do first is I want everybody to notice, now I'm not going to, a little trick here, it's hard to find the range of this function, but certainly the domain, I'm not allowed to let x be 2. Okay, so I'm going to postpone finding the range of the original function. The way I'm actually going to find the domain of the original function is minus infinity to 2 union 2 to infinity. That actually becomes the range of the inverse. Now the way that I find the range of the original function is actually to find the inverse function and find its domain. The domain of the inverse would be the range of the original. So I'll show you how to do that once I find the inverse function. Okay, so first I'm going to show f is 1 to 1. So same thing as we were doing above. You assume that f of a equals f of b, and I want to show that a equals b. Okay, so now f of a is 2 over a minus 2 plus 1, and that's going to equal f of b, which is 2 over b minus 2 plus 1. If you subtract 1 from both sides, you get 2 over a minus 2 is equal to 2 over b minus 2. And then I'm going to cross multiply. Okay, so really I'm multiplying both sides by b minus 2 and both sides by a minus 2, but really I'm just doing this little, whenever you have two fractions equal to each other, you can cross multiply. So 2 times b minus 2 equals 2 times a minus 2. And it does, I'll let everybody verify this on their own, but if you divide both sides by 2 and then add 2 to both sides, you will get a equals b. Therefore, the function is 1 to 1. Okay. Now let's go about finding the inverse function. Okay. So what you do is you take the original function 2 over x minus 2 plus 1, you set it equal to y, and then I'm going to try and solve for x. So I'm going to subtract 1 from both sides. Then I'm going to multiply both sides by x minus 2. Okay, so I get 2 is equal to y minus 1 times x minus 2. And then I'll show you this step. If I'm trying to solve for x, what I'm going to do is I'm going to divide both sides by y minus 1, which cancels it on the left. So now what I have is that x minus 2 equals 2 over y minus 1. Sorry for running out of room here. Then I'm going to add 2 to both sides. Okay, and therefore, okay, and then the step 2 of finding the inverse says replace x with f inverse of y. That's 2 over y minus 1 plus 2. Okay, so there's the inverse function. Okay. The inverse in terms of y. Now, let me step back for a second. Now remember the domain. Remember the domain of the original function was negative infinity to 2 union 2 to infinity. Now I just found the inverse function, f inverse of y, was equal to hold on, I gotta think here for a second what this was. Y minus 1. So it was 2 over y minus 1 plus 2. And now notice the domain of this is everything but positive 1. Sorry, that's I gotta write that better. I don't like that. So the domain of the inverse function is negative infinity to 1 union 1, 2. Oh, these stylus pens are pain. There we go. So that's the domain of the inverse. You just can't divide by 0, so y can't be 1. That becomes the range of the original function. And the domain of the original function becomes the range of the inverse. Okay. So actually, if a function is 1 to 1, finding the range just comes down to finding the domain of the inverse. Okay. So that's how I got that there. Now the last part, and I haven't done this yet, is how to verify this property for inverse functions. Okay. So when you compose a function when it's inverse, you're supposed to get the input back. So I'm going to write down both functions again. So f of x was, shoot, hold on, I got to go back and look because my memory is terrible. So 2 over x minus 2 plus 1. So f of x was 2 over x minus 2 plus 1. And now I know the inverse as a function of y was 2 over y minus 1 plus 2. Okay? And now I'm going to do f inverse of f of x, and I'm going to show that this equals x. So replace f of x with its equation. Okay. And then this whole piece right here. Okay, so this input now is going to get plugged into the inverse for y. This might look a little bit messy, but should be able to have room to do this. So this now equals 2 divided by, and this whole thing becomes the y. So that's the y. I subtract 1, and then I add 2. Now what you're going to notice is the 1's are going to cancel in the denominator. So this is 2 divided by 2 over x minus 2 plus 2. Now, for this part right here, dividing by a fraction is the same as multiplying by the reciprocal. So instead of dividing by 2 over x minus 2, I can multiply by x minus 2 over 2. Still have to add 2. The 2's will cancel. These 2's will cancel. And you're just left with x. Okay? Now I can do it, so that verifies the first part. Okay, now I can do it for, now I can verify the second one. So now I can verify the second one. So just remember f of x was 2 over x minus 2 plus 1. F inverse of y was 2 over y minus 1 plus 2. And this time I'm going to do f of f inverse of y. So I'm going to replace the inside with the inverse function. Okay. And then now the way this works is you're going to take this inverse function and plug it in for x. So this equals 2 divided by, that whole expression gets plugged in for x. So that's the x. You subtract 2 and you add 1. You'll notice this 2 and this minus 2 cancel. So now this is equal to 2 over y minus 1 plus 1. Dividing by a fraction is the same as multiplying 2 by the reciprocal. The 2's cancel, the minus 1 and the plus 1 cancel, and you end up getting y. Okay. So, when you compose a function with its inverse, you just get the original input back. So hopefully everybody, for the most part, got the gist from the video. If anybody start working on the homework, if anybody has questions, we'll certainly go over those in class. I've posted my math lab homework, and I've posted written homework problems. If anybody has any other questions or needs any other help, make sure to let me know. I'll see everybody in class on Monday. Hope you had a good weekend. Thank you.